Welcome to my lecture series on the chemistry of main group elements. In my last lecture, I was discussing about the effective nuclear charge. So, let me continue from where I had stopped. I had just mentioned that the magnitude of the influence of the nucleus on electrons decreases with the increase in the size of atoms as added electrons are farther from the nucleus. This is essentially due to the shielding or screening of nuclear charge by inner or core electrons. That means we should find a method to calculate or estimate the effective nuclear charge by each and every electron around the nucleus. For this one, Slater has suggested some rules. Let us look into those things. Slater's rule and the effective nuclear charge. How Slater estimates is given here. So, he provides a method to estimate the effective nuclear charge Z effective from the real number of protons in the nucleus, that is equivalent to the atomic number, and the effective shielding of electrons in each orbital. Slater's rules are simple and very easy to follow. For example, you can look into the formula he has given. The shielding or screening constant S is nothing but the sigma Ni Si, where Ni is the number of electrons in a specific shell and subshell, and Si is the shielding of electrons subject to Slater's rules. And then by knowing the screening constant and simply by subtracting the value of screening constant from the atomic number, one can estimate the effective nuclear charge Z effective. So, Z effective is nothing but Z minus S, and one should remember the effective nuclear charge Z effective is always less than the actual nuclear charge Z due to the repulsive interaction between the core and the valence electrons. So, how to calculate effective nuclear charge? We have to follow simple 3 steps. First, one has to write down the electronic configuration of the atom as shown there. You can see here 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, something like this. And also I have added some parentheses at regular interval. It has some significance. Step 2 is identify the electron for which Z effective has to be determined, and ignore all electrons in higher groups or on the right side of the electron in consideration, because whatever the electrons we have on the right side are not coming in between the nucleus and the electrons we are considering. And third step is shielding experienced by S or P and D or F will be very different. So, that means there exist 2 different cases. We call them as case 1 and case 2. How to determine the shielding constant is given in case 1. For example, electrons within the same group shield to an extent of 0.35 except the 1s electron. In that one it is estimated to be 0.30, and electrons in n-1 group shield to an extent of 0.85, and electrons in n-2 group or lower groups shield to an extent of 1. That means all electrons should be together multiplied by 1 to get that screening constant. In case of case 2, we are considering for determining the screening constant for D and F electrons. So, here electrons in the same group shield to an extent of 0.35. This is very similar to what we mentioned about S and P, and electrons in lower groups shield to an extent of 1. So, that is the difference between S and P and D and F. In case of S and P, we are considering both n-1 group and n-2 group and the rest as separate units, whereas in case of D and F only we are considering 2 cases. One is the shielding of the electrons within the same group, and the shieldings in lower group, no matter how many electrons are there, simply they have to be multiplied by 1 to get the value. So, this figure depicts very nicely Slater's rules. You can see here in case of D and F block, the electrons in the same group will contribute 0.35 and rest of the elements will be simply contributing 1 towards the screening, whereas in case of S and P electrons within the same group the shielding is to an extent of 0.35, and in case of n minus 1 shell it is 0.85, and n minus 2 and lower it is 1. So, let us look into some examples to examine authenticity of Slater's rules. The first one is find out screening constant and effective nuclear charge of p electron of boron. What we should do is, first we should write the electronic configuration for boron atom. So, electronic configuration of boron atom is 1s2, 2s2 and 2p1. So, the consideration here is the p electron, for which we have to calculate the effective nuclear charge as well as screening constant. Let us use the simple formula given by Slater. S of 2p is asked. For this one should write first n minus 2 electrons and n minus 1 electrons and plus n electrons. So, here n minus 2 we do not have anything, zero, plus we have 2 electrons here 0.85 into 2, and then we have here only 1 electron is there, and in this case we have 2 electrons are there 0.35 into 2. So, now this will come around 0 plus total will be 2.4. So, now this is, you can call it as S or sigma. So, now Z effective equals Z, the atomic number, minus sigma or S. So, here in case of boron atomic number is 5 minus 2.40, which will give you 2.60. So, this is the effective nuclear charge for p electron of boron. So, let us look into the same values for 2p electron in oxygen atom. Find out screening constant or shielding constant and effective nuclear charge of a 2p electron in oxygen atom. For this again we have to do the same exercise. First we should write the electronic configuration of oxygen, that is 1s2, 2s2 and 2p4. So, here if you use the same analogy, we are calculating the screening constant for 2p electron. So, to make you familiar, I repeat again, n minus 2 electron plus n minus 1 electron plus n electrons. So, here we do not have any electrons n minus 2. So, 1.00 into 0 plus here we have 2 electrons are there in n minus 1. So, that is in 1s2 0.85 into 2 plus we have about 5 electrons in the same group, that is 0.35 into 5. So, out of 6 electrons we are considering one of the p electron, the remaining 5 electrons will be screening it. So, that is 0.35 into 5. So, this will come around 3.45. So, now Z effective of 2p electron of oxygen is 8 minus 3.45, that is equivalent to 4.55. So, this is the effective nuclear charge for 2p electron in oxygen atom. So, this is how one can calculate without any problem. Let us look into one more example here. determine the screening constant and effective nuclear charge for a 3D electron in the bromine atom. Same exercise one has to do it. Let us write the electronic configuration of bromine. One S2, 2S2, 2p6, 3S2, 3p6, 3d10, 4S2, 4p5. Since the electron in consideration is from 3D, we have to find out the 3D electron screening constant. For that one, sigma equals 1.00 into 10 plus 1.00 into 8 plus 0.35 into 9. So, here 4s2, 4p5 are on the right side of d orbital. So, they should be ignored as they are not contributing towards the screening constant. So, we have to consider only here 1s2, 2s2, 2p6, 3s2, 3p6 and within the group these 9 electrons. That is what I have written here. So, this is for these 9 electrons, 1 electron we are considering and then it is total 18. I have simplified by writing 10 and 8. Essentially, one can also write this as 1.00 into 18. So, 18 will account for this 8 plus 8, 16 plus 2, 18 and plus 3, 5 into 9. So, this comes around 21.15. So, Z effective for 3D electron in case of bromine is, bromine atomic number is 35 minus 21.15 will give a value of 13.85. So, this is essentially the effective nuclear charge of d electron in case of bromine. So, this is how one can calculate the effective nuclear charge using simple and easy to follow Slater's rules. So, let us look into another question here. It is a very interesting question. SF2, SF6, sulfur difluoride and sulfur hexafluoride both exist, whereas sulfur dichloride exists and sulfur hexachloride is not known. Let us look into the enthalpy of formation of these 4 molecules. The values are given in kilojoules per mole. In case of SF2, it is minus 298 kilojoules per mole, whereas in case of SF6, it is minus 1220 kilojoules per mole, whereas in case of sulfur dichloride is minus 49 and in case of sulfur hexachloride is minus 74. Of course, in both the cases compared to SF2, SF6 is exothermic. Similarly, in case of SCl2, SCl6 formation is exothermic, but it does not give satisfactory answer for not existence of SCl6. So, let us look into some more information. So, although the formation of SCl6 is more exothermic just by looking into the values of SCl2 to SCl6, that is 49 and 74, SCl cannot be, sulfur hexachloride cannot be prepared under normal conditions. The explanation can be found simply by considering bond enthalpies of sulfur halogen bonds in the series given here. Just focus your attention here. The bond enthalpy in case of SF2 is 367 kilojoules per mole and bond enthalpy in case of SF6 is very less, that is 329 kilojoules per mole, and in case of SCl2 it is 271 kilojoules per mole. That means, how to explain the decrease in the bond enthalpy between SF2 and SF6? Of course, one can explain using the steric crowding of 6 fluorine atoms which are loaded with 8 electron each. which generates enormous repulsion between the crowded F atoms. So, a similar decrease is anticipated in case of SCl6 compared to SCl2. This weak bond is one factor that is makes to preparation Cl6 or sulfur hexachloride preparation bit difficult. In addition, one can also consider the entropy change. Entropy change in both the cases are negative. For example, one sulfur is interacting with 3 molecules of chlorine gas to generate one SCl6, that means the entropy is very negative, and so that means essentially the steric crowding and the entropy effect goes against the formation of SCl6. That is the reason SCl6 is not known. However, in case of SF6, because of the enthalpy of formation is little larger, so SF6 can be made easily, but under normal circumstances at ambient condition SF6 is stable, but higher temperature it decomposes to form lower halides or lower fluorides. So, there is another question. Without using the periodic table, write down the electronic configuration and the group number for the elements with the atomic number shown below. So, how to do that one? For this one, it appears like it is very complicated, but once if you are familiar with electronic configuration and also if you are familiar with Hofbauer principle, it is not at all difficult to write the electronic configuration for any value. For example, let us look into this Hofbauer principle that gives the relative energy of all the orbitals. If we follow this sequence that is shown, the writing the electronic configuration for any atomic number would be very easy. Okay. So, let us look into the electron affinity. Okay. The question here is given for 2 sets of chemical species. Arrange each of the following set of chemical species in the decreasing order of their electron affinity. So, just we have to see the 2 groups. In one group, essentially germanium, silicon and carbon are given. All these 3 elements belongs to group 14 in the same order. For example, carbon, silicon and germanium are written in the decreasing order of their atomic number, and in case B it is chlorine, chloride ion and chloride anion and chloride cation is given. So, let us try to make an attempt to write the decreasing order of their electron affinity. It is very simple. We have to look into the effective nuclear charge and what would happen to the electronegativity of removal or addition of electron. One should follow simply that one. In case of A, it is very straightforward. A given elements are germanium, silicon and carbon. Simply we can follow the same sequence as this one. So, here electronegativity is decreasing down the group. So, electron affinity also decreasing down the group. This is the answer. In case of B, it should be other way around. Cl plus has more electron affinity compared to Cl, and that in turn compared to Cl minus. So, this is the decreasing order of their electron affinity for both the set of chemical species given here. Let us look into one more question here. So, arrange each of the following set of chemical species in the order of decreasing the radius. Let us consider the first row at a time, one row at a time. In the first set, we have sodium, magnesium, argon and phosphorus. In the second one, we have iodide, Ba2 plus, Cs plus and xenon. In the third series, we have carbon, aluminum, fluorine and silicon, and in the last one we have argon, K plus, S2 minus and Cl minus ions. Let us start one at a time. So, first we have to identify the elements present in the series, and we have to write down the atomic number, and by looking to the atomic number and their relative positions in the periodic table, we should be able to write it without any problem. For the first one, the answer is So, this is the order. Similarly, for the second one, the order is xenon, then I minus and Cs plus and then barium 2 plus. In series C, it is aluminum, silicon, carbon and then fluorine. In the last series, it is argon, then S2 minus sulfide ion and then chloride ion and then K plus. So, here we had discussed in the previous lecture and also my first lecture about the relative variations in the radius, atomic radii and covalent radii and all those things by simply identifying the position of these elements in the periodic table, and by adding a removal of electron to generate the species shown, one should be able to write in this sequence without any problem again. So, first write down the electronic configuration using box diagram and mark the electrons asked for writing the quantum numbers. So, here the question asked is to write quantum number sets for the third and the 8th electron of the fluorine atom. That means, first we have to write the electronic configuration and we have to identify the electrons for which we have to write all the quantum numbers. So, it is convenient to write in the form of box. So, label them 1s, 2s and 2p and then you fill it. So, now we have about 9 electrons are there. In 9 electrons we have to identify the third electron is from the 2s and the 9th electron is from the 2p series. So, for this one we have to write now. So, third electron is in the 2s orbital, its quantum numbers are n equals 2, L equals 0, ML equals 0 and MS equals plus or minus half. Okay. So, similarly, quantum number for the 8th electron is can be written here, again n equals, this is for the third electron, this is for the 8th electron, n equals 2, L equals 1, ML equals minus 1, 0 or plus 1 and MS equals plus or minus half. So, this is how one can write all the quantum numbers for any electron in a atom. So, now another question is there. Arrange each of the following set of elements in the increasing order of their first ionization enthalpies, i.e. 1. Okay. So, I repeat again, arrange each of the following set of elements in the increasing order of their first ionization enthalpy. So, we have 4 sets. In the first set we have potassium, calcium and rubidium. Next we have krypton, helium and argon, and third one we have iodine, xenon and cesium. In the last series we have antimony, tellurium and tin. Again we have to identify their position in the periodic table, whether they belong to the same group or in a same period or from different groups. Once after identifying and knowing their atomic number, we should be able to write taking clue from the periodic trends. First one answer is rubidium, similarly for the second one it is krypton, argon and helium. Third one cesium is less than, iodine is less than xenon, and the last one tin is less than, antimony is less than tellurium. So, like this one should be able to answer any question, and here I complete the classification of elements and their periodic trends and periodic properties. In my next lecture, I will be discussing about structure and bonding aspects, where I will be introducing various bonding concepts to explain how one can understand physical and chemical properties of molecules of main group elements and look into their chemical behavior and chemical properties through structure and bonding concepts. Have a pleasant reading. Thank you very much.